So there are multiple ways for us to represent complex numbers. So what I'm going to do here in the middle of my page is draw a complex plane. The horizontal axis of our complex plane corresponds to real numbers, and the vertical axis of our complex plane corresponds to imaginary numbers. So the first representation that I want to talk about is the rectangular form. So let's say that I have a complex number, and I'm going to call it A. Anytime I have a bar over a quantity like that, it means I'm dealing with a complex number, okay? In textbooks and things, complex numbers are usually expressed in boldface, but I don't have the capability of writing in boldface. So I'm going to put a bar over the top to let you know when I'm talking about a complex number. So in rectangular form, complex numbers are expressed as a real portion, which I'm going to call lowercase a in this case, plus jb. So the real part of complex number a is lowercase a, and the imaginary part of complex number a is lowercase b. J is the imaginary operator, which is equal to the square root of -1. So in your pre-calculus classes and all that kind of stuff, you are very likely introduced to the imaginary operator I being equal to the square root of -1. But in electrical engineering, where I represents current, that would be far too confusing. So we have adapted lowercase j, all right? So when you're typing stuff into your calculator, I fully expect you to find the I for the imaginary operator button. But in this class, we're going to refer to that operator as j, so as to not be any more confusing than we have to be, okay? So I could represent this rectangular form complex number on my complex plane here by going A units in the real direction and then B units in the imaginary direction. So that might look something like this, where the projection onto the real axis is A, and the projection onto the imaginary axis is B. As we can see, our complex number forms an angle in relation to the horizontal axis. So I'm going to call this angle theta A, which allows me to come up with an alternative way to express a complex number. So we're going to call it the polar form representation. Actually, let's do the exponential and the polar at the same time, but I'll put the exponential over here. So the exponential form of a complex number and the polar form of a complex number contain literally the exact same information, just expressed in slightly different ways. So we could say that our complex number A, the same complex number that we're dealing with in rectangular form, is the magnitude of complex number A, or the length of that two-dimensional vector, times e to the j theta A. And in polar form, we would represent this relationship as simply the magnitude with an angle operator, theta A. So the polar form representation of a complex number is just shorthand notation for the exponential form, okay? It's literally the exact same thing. We just throw away that e to the j bit because it's common. We don't need to continue writing it over and over and over again. Your calculators take inputs of complex numbers in either rectangular form or polar form. If you give it to them in exponential form, it will freak out, okay? And it's just the way that the calculator does complex math. If you put that e to the j in, it tries to interpret it in a way differently than kind of what's needed. So when we're putting numbers in our calculator, it's always going to be the far right-hand representation or the far left-hand representation, okay? So it may be useful for us to be able to convert back and forth between these two representations, all right? So let's develop our relationships for the exponential parts in terms of our rectangular parts first, and then we'll go back the other way around, okay? So using simple trig identities, it should be fairly easy to see that the magnitude of A is the square root of the real part squared plus the imaginary part squared. This is literally just Pythagorean theorem. The angle theta A, again using trig identities, is nothing more than the inverse tangent of the imaginary part over the real part. So that tells us how to get the components of both the exponential form and polar form from a rectangular form. If we wanted to go the other way around, we could see that lowercase a is simply the magnitude of complex number a times the cosine of theta a, and the imaginary part b is simply the magnitude of the complex number a times the sine. So the projection onto the real axis and the projection onto the imaginary axis. For those of you who have recently taken Physics 201 and done a bunch of dot products and stuff like that, it's effectively all that we're doing. All right, so any questions thus far? Anybody got anything? All right, so let's take a quick break before we introduce more things and work an example problem that effectively ruins this and then talk about why it ruins it, because that's the kind of guy I am. All right. So let's say that we have a complex number. Let's call it x is equal to -5 plus j7. Obviously, this is a rectangular form complex number. What I want to know is how we would express this in either polar or exponential form. Let's actually do both just for the sake of argument, okay? So the magnitude of x is just going to be the square root of -5 squared plus 7 squared is going to be the square root of whatever 25 and 49 make. So it's like 74, is that right? All right. And if we wanted to make this a decimal number, we could, but I'm lazy and I'm not going to. I don't think that can be particularly reduced. Angle theta x is the inverse tangent of b over a. So the imaginary part is +7. The real part is -5. Let's do this operation real quick. Inverse tangent, 7 over -5. And I get -54.462 degrees. And if my calculator were in radian mode, I could get the answer in radian mode, but I'm also lazy there and not going to do it. Typically speaking, electrical engineers work in polar form with our angle expressed in degrees. So, can anybody tell me what's wrong with this? Angle being negative isn't necessarily a problem. If we plotted this, we would have a number. So -5 in the real direction, +7 in the imaginary direction. That means that x should lie somewhere over here in quadrant 2. But according to our results, we get x, and I'm just going to put a prime here, meaning that it's not actually x, in quadrant 4. Okay. The problem here in doing this hand calculation is that your calculator cannot tell the difference between inverse tangent of -7 over +5 and inverse tangent of +7 over -5. The inverse tangent operation will always give you an angle that lies in either quadrant 1 or quadrant 4. So to correct this, we would actually have to add or subtract 180 degrees. So I'm just going to put this right here. Plus or minus 180 degrees would give us whatever our correct angle is supposed to be, right? We simply just need to rotate that other half circle around to force the answer to be in quadrant 2. No, you only have to do this if the complex number lies in quadrant 2 or quadrant 3. But let me, before you start worrying about that, let me explain something, okay? Hand calculations like this are useful to kind of understand the inner workings of what complex numbers are and how they behave. That being said, your calculator is perfectly capable of converting from a rectangular form complex number to a polar form complex number and giving you the correct answer without having to do this manipulation, okay? A large part of this lecture is going to be, how do I make my calculator do the work for me? Legitimately, okay? So, for those of you with TI calculators, we could type in -5 plus 7, and then press the pi button 3 times to get the imaginary operator I. If we then press second and the pi button, it pulls up our complex menu. And we can scroll down to option 4, which tells the calculator to express the result of that number in polar form. And we get 8.602, which is the square root of 74, angle positive 125.537 degrees, which is exactly what we would get if we took -54.462 and added 180 degrees to it. So if you got a TI calculator and you weren't able to follow, raise your hand and I'll come by and show you what I just did. And then I'm going to do it for those of you with Casios and then tell you how to do it. And if you have a problem, again, I'll come and show you what to do. So anybody with a TI calculator? Which is the third? I honestly don't. Let me see. All right, so for those of you who have Casio calculators, it's a little bit more complicated. To do these operations, you need to first put your calculator in complex mode. So that involves pressing the mode button and then pressing the number 2. Once you have your calculator set in the complex mode, we would simply type in -5 plus 7, and then we would press the ENG, or the engineering button, which gives us our imaginary operator I. Now, to convert this to a polar form complex number, the way to do it depends on which calculator you have. If you have the Casio FX115, you need to press Shift 2, and then press to bring up your options, and then press 3, which will convert to a polar form complex number. If you have a Casio 991, once you have -5 plus J7 typed in, you literally press the options button, and it'll bring up the menu that will allow you to switch from a polar form complex number, or excuse me, from a rectangular form complex number to a polar form. Let's borrow your calculator real quick to tell you what button. Scroll down 1 and then press 1. Okay. Why did that go away? Yeah, so you press the option button, scroll down 1 menu, and then press the 1 key. And the projector went out, so I don't know what I did to mess that up. Well, that's not right. Okay, there we go. All right, so hopefully we have all figured out how to convert a rectangular form complex number into a polar form complex number using our calculators at this point. Now, just for the sake of, I don't know, robustness or inclusivity or whatever, let's go the other way around. Let's start with a polar form complex number and then convert it into a rectangular form. So let's say that we have a complex number y that is 10 angle 15 degrees, okay? So to type that in for you Casio users, you would do 10 and then shift the negative key. That should give you the angle operator. And then you would literally just type in 15 if your calculator is set to work in degree mode. For those of you with the 991s, you would then hit option, scroll down, and then hit 2. For those of you with the 115s, you hit shift 2 to bring up the complex option window. and then press 4 to convert the answer into rectangular form. The result should be 9.659 plus J 2.588. For those of you with the TIs, type your number in. The angle operator is got by pressing the second pi key. So press second, then press pi, then press 1, and that gives you your angle operator. And then to convert, I want to say that it's option 4. I don't have my calculator in front of me. It's either option 4 or 5.
It's
5, okay. Anybody at all having difficulty converting from polar to rectangular, raise your hand and I'll come show you how to do it on your calculator. So, we're not in. So sorry, okay, for you, it's shift engineering, sorry. Okay, so for the 991, excuse me, the 991 people, the imaginary operator is shift engineering. So engineering gives you I, shift gives you angle. For the 115 people, it's just negative. Sorry. Anybody else need help with their calculators? All right, so the next thing I want to talk about is mathematical operations using complex numbers, okay? So the first operation that we are going to talk about is the conjugate operation. And this is unique to complex numbers, all right? So again, I'm going to draw my little complex plane here, where this is my real axis, and this is my imaginary axis. And I'm going to have some complex number A, whose projection onto the real axis is lowercase a, whose projection onto the imaginary axis is lowercase b, and it forms some angle theta A with the real axis, okay? So A is defined as A plus JB in rectangular form, and as A is equal to A e to the J theta A in exponential form, which is the same as A angle theta A in polar form. To get the complex conjugate of our number, we simply rotate our complex number about the horizontal axis. So that means A conjugate will be this guy down here, where the conjugate operation is denoted by placing an asterisk after the number. And we can see by inspection that A conjugate is A in the real direction, and it's minus B in the imaginary direction. So to do the complex conjugate operation on a rectangular form complex number, we simply change the sign on the imaginary part. for our polar form complex number, it should be fairly obvious to see that the angle formed with our positive horizontal axis is now just going to be negative theta A, such that our complex conjugate operation for exponential form and polar form complex numbers is carried out simply by changing the sign on the angle. So this is a conjugate operation. All it is, rectangular form, change the sign on the bit with the J, polar and exponential form, change the sign on the angle. That's it. Okay. Now let's talk about mathematical operations we're probably a bit more familiar with, like addition. So if I have a complex number A equal to A plus JB, and I have a complex number B is equal to C plus JD, then A plus B looks like A plus JB plus C plus JD, and grouping real terms together, this gives us A plus C, and now grouping our imaginary terms together, J times the quantity B plus B. This is just like adding vectors in your Physics 201 class, right? The real parts are vectors in the X direction or in the real direction. The imaginary parts are vectors in the Y direction, and you just add the X components together, add the Y components together, and you get your resultant. Subtraction is effectively the exact same thing as addition, but there's a negative sign thrown in the mix. So if we have the same complex number, A is A plus JB, and B is C plus JD, then A minus B looks like A plus JB minus C plus JD, giving us A minus C plus J B minus D. If you are going to do addition and subtraction by hand, you have to do it using rectangular form complex numbers. There is not an easy way to perform the operations of addition or subtraction using polar form complex numbers, unfortunately. All right. Does anybody have any question on this bit right here? Hopefully fairly straightforward. All right. So let's talk about multiplication next. So if we have A is equal to A plus JB and B is equal to C plus JD, then, sorry, they shouldn't have magnitudes on them, it's my fault. A, B is simply me multiplying those two things. Now I want to be clear here. I don't typically write a dot in the middle to indicate multiplication because these complex numbers are vectors, but the dot product is not something that exists in the complex number space. Nor do I write a cross B or a XB, because that could potentially look like me taking the cross product of these two vectors, which also is not a thing that exists. So if I write two complex numbers beside each other, I am implying that they are multiplied by each other. Okay. So this is going to look like A plus JB times C plus JD. And I'm simply going to FOIL this out, right? So that's going to give me A times C plus JAD plus JBC plus J squared BD. Now let's take a moment to look at this term J squared. And actually other powers of J as well. So I'm going to put J to the first power here in the middle. And as a reminder, this is equal to the square root of -1. J squared is just J times J. So this should be -1. J cubed is just J times J squared. So it's -J. J to the fourth power is J squared times J squared, +1. And if I had J to the fifth power, that's just J to the fourth, which is 1 times J. And so effectively this cycle just repeats itself, okay? I can go the other direction as well. J to the 0th power is 1, because anything to the 0th power is 1. J to the -1 power is 1 over the square root of -1. I could multiply that by the square root of -1 over the square root of -1, and this would give me -J. J to the -2 is, let's see, -J. Oh, I'm sorry, this should be -1. Yeah, because that's 1 over the square root of 1 times 1 over the square root of -1, which is just 1 over -1 or -1, and so forth. So it repeats. It literally just cycles through these over and over and over again. So there's only 4 possible things that J to any power can be. J itself, -1, -J, or +1. It's always going to have one of those 4 values. All right. So we can see that that J squared term is actually a real number, giving us AC minus BD plus J AD plus BC. Everybody okay with that? So multiplication using rectangular form complex numbers, tedious, but doable. Let's look at it using exponential form complex numbers. So if we have A is equal to the magnitude of A e to the j theta a, and b expressed as the magnitude of b e to the j theta b, then a multiplied by b just looks like the magnitude of a e to the j theta a times the magnitude of b e to the j theta b, or the magnitude of a multiplied by the magnitude of b times e to the j theta a plus theta b. So multiplication is typically easier to do using exponential or polar form complex numbers, right? The result of multiplication using polar form complex numbers is simply the magnitude of A, the magnitude of B, angle theta A plus theta B. Since again, our polar form representation is nothing more than a shorthand notation of our exponential form. They have to have the same information, or contain the same information. All right, so any questions regarding multiplication? All right, now let's do division. This is going to be our last mathematical operation. So if I have A is equal to A plus JB, and dang it, I keep writing these magnitudes when I don't need them. My apologies. B is equal to C plus JD. A divided by B is going to look like, let me give myself some room here. A plus JB divided by C plus JB. Now this is a little bit of a problem because our expectation here is that if we take two rectangular form complex numbers and divide them, the resultant should be a rectangular form complex number. How we're going to force that to happen is by multiplying by the conjugate of the denominator divided by the conjugate of the denominator. So B conjugate would be C minus JD and let's look at the denominator first. We're going to have C times C, so C squared. Then we're going to have C times negative JD, so that's negative JCD. Then we have positive JD times positive C, so that's plus JCD. And then finally, we have JD times negative JD, which is negative J squared D squared. In our numerator, this is going to look like AC minus JAD plus JBC minus J squared BD. And we can simplify those J squareds into -1 and also observe that this negative JCD and this positive JCD cancel each other out, giving us AC. So minus J squared is minus -1, or positive BD plus J BC minus AD, and then this whole thing is over E squared plus B squared. So rectangular form complex number division is, I don't want to say difficult, but it's definitely a pain in the butt. I would not advise doing it this way, but it does bring us to a very interesting tangent here real quick that I want to cover before we get into how to do this using polar form complex numbers, okay? So if I have a complex number, let's just say A, and I multiply that complex number by its conjugate, what happens? Well, we can see that it's simply the real part squared plus the imaginary part squared, right? So this would look like A squared plus B squared, which is nothing more than the magnitude of A quantity squared. So anytime we multiply a complex number by its complex conjugate, the result of that operation is the magnitude of that complex number squared. We will use that little identity at multiple points in this class. So finally here, let's do division using exponential form complex numbers. So if we have A is equal to the magnitude of A, e to the j theta A, and B is equal to the magnitude of B, e to the j theta B, then A divided by B is the magnitude of A divided by the magnitude of B, e to the j theta A divided by e to the j theta B, which can be simplified as the magnitude of A divided by the magnitude of B, e to the j theta A minus theta B, or in polar form, magnitude of A over magnitude of B angle theta A minus theta B. So it should be fairly obvious here that division using polar form complex numbers or exponential complex form numbers is much easier than division using rectangular form numbers. All right, so I have laid out all of the ways to do these different mathematical operations by hand, because we are going to rely on some of the identities and things that I've introduced here in later classes. In practice, your calculator does not care if you put your complex numbers in rectangular form or polar form, and it is able to do all of these operations using a mix of polar form and rectangular form complex numbers if that's how you happen to enter it in, and it will give you the answer in either polar form or polar form or rectangular form, depending on what the settings of your calculator are, okay? So for your homework assignments, all that kind of good stuff, you don't need to go, oh, I'm going to do multiplication, so I need to convert this. I need to make sure everything's in terms of a polar form complex number. Just let your calculator literally do its job. But sometimes we are going to have to rely on these identities to make sense of what's going on in this class, which is why I take almost the better part of an hour explaining how to do it and then tell you, but you're just going to use your calculator. So, anybody have any questions about this complex number review? All righty, so that's enough out of me for today then. Take the next 10, 15 minutes or so and do the in-class assignment using your calculator. If you have any questions about anything, I'll be happy to come by and explain what to do.